Okay, so welcome to the second part of the course. So now, we have motivated why somehow, we are going to look at curves in general. And so these curves, as I said, I want to consider models which are smooth, projective, and absolutely reducible. So we are going to look today, this is going to be the second part, at elementary properties of smooth, absolutely reducible projective curves. Okay, smooth, I have motivated it. Absolutely reducible, I think, it was quite motivated during the first lecture as well, because we have seen, if you have reducibility over the field, then, it's like you're considering two different curves. Now you have as much space as you want, because you're not restricting inside the plane. So, if you can add as many pieces as you want, of course, the number of points can be as big as you want, so it's not really interesting. And if it would be irreducible, but not absolutely irreducible, we have seen also that, in general, this gives you quite bad curves in terms of the number of points, because the points are going to be exchanged between the different components, so all the points rational points are going to be only in the intersections. And so there are going to be very few in general. And projective, I motivated a bit yesterday, but we will see even more today why it is so important, to have this property, in order to give, nice things. So let's focus first on smooth. Why smooth is so nice? So, if you look in the notes on page 15, then, when you introduce something which is the local ring at a point P in C. So indeed, the notion of being smooth, so regular or non-singular, is something which is local. In particular, you could restrict to an affine model of the curve, just locally looking at an affine chart. And even closer, you can look at the local ring. And the local ring, so which is denoted OP in the course, this is going to be the set of all the functions on the curve, such that you can write f as the quotient of f1 over f2, where f1, f2 belong to the function field, to the coordinate ring, sorry, and so this here I'm really speaking about affine curves. And I'm asking that f2 at P is not 0. So it is a local ring, indeed, because it contains a unique maximal ideal. So the unique maximal ideal, I'm going to denote it MP, and it's easy to see that it's the set of F inside K bar of C, such that F at P is 0. All right? What more? So the nice thing is that once you have these things, you can see that when we introduce the notion of being regular, you can introduce it in terms of the equations and so in terms of the Jacobian criteria, but you can also look at it in terms of more intrinsically, in terms of really things which depend locally on the point. And P is regular if and only if the dimension of MP over MP squared as what? As a vector space given by over the residual field OP over MP, if this is 1. Okay? And now what we are going to do is we are going to do a bit of algebra to show that in the case of curves, having this property of the dimension of mp over mp square equal 1 is really nice because it gives a lot of structure to the local ring OP. And so what we are going to prove is the following lemma. So OP is actually a discrete valuation ring. So what does it mean? It means that there exists a valuation, so V, which go from K. So what is K? This is K bar of C, stars, so without the 0, which surject on Z, and which has the property that V of x, y is V of x plus V of y, and V of x plus y is bigger than the minimum of V of x and V of y. And the last thing that you want is that OP is going to be the set of x in K star such that the valuation of x is greater or equal to 0, union 0. Okay? So in order to do this, we are going to do a bit of algebra, and there is one important lemma in commutative algebra that we are going to use is Nakayama's lemma. But here I'm going to state it in the form really that I need. I mean, it's a more there is something more general that you can find in the literature. For instance, there are plenty of books on commutative algebra, ATIA books, for instance. So if I take, let A be a Noetherian local ring with a maximal ideal M such that the dimension of M over M square is 1. Then what you can prove is that M is principal. Okay, so how do you do that? Well, first, you have a Noetherian ring. And this is always nice because it means that all your ideals are going to be finitely generated. So let's take generator x1, xn for M, and with n assume greater or equal to 2. And we take the smallest possible, okay? And if we get a contradiction, then we are done. The other thing I can say is that I also can assume that x1 doesn't belong to M square. Okay, there is necessarily one of the x1, xn which doesn't belong to M square because M is not M square, otherwise the dimension would not be 1. Okay, so what can I do now? So now I know that x1 is going to generate M over M square as a K vector space where K is A divided by M because the dimension is 1. So what I can do is I can now look at xn. Xn is in M, and so I can express it as x1 plus a sum of element inside M square. So it's going to be x1 plus a sum of element inside M square. So this is a sum that I can write alpha I xi from I1 to n with alpha I inside n. And now I win, because you can do the following. You can write xn times 1 minus alpha n is equal to x1 plus a sum from in to n minus 1 of alpha I xi. And what you know is that as alpha n is in M, 1 minus alpha m is invertible. I mean, this is really easy to prove. You just have to use that m is the unique maximal ideal. So this is invertible. But then, yeah, this is the conclusion. Actually, xn is already inside the ideal generated by x1 to xn minus 1. And then you're done, because, I mean, you had assumed that n was minimal, so it should not be. So the conclusion is that m is generated by x1, so it is principal. Okay. So now, I mean, we go on a bit. I mean, from this, the first thing that you can look, I mean, you can look also at the quotient now of powers of mn over mn plus 1. And you can look at the dimension, again, of this, and just writing that m is x1 plus m squared. For the same reason, I mean, you do a recursion, and you get that the dimension of these spaces are also 1. And because they are also 1, you can apply the same proof as you had over there to show that m to the n is also x1 to the n simply. Okay. Another property that you can prove again by the same kind of argument, that now you take the intersection of all the powers of n. And I say that this intersection, I mean, it's an ideal that I'm going to call A. This is actually 0. I mean, how can you prove that? Again, I mean, you can try yourself. I mean, the idea is just to say, if you look at A is equal to A squared. So the proof is again to say that A equal to A squared and use the same proof as Nakayama. So just do the exercise here and you will find it. Okay, and now what more? All right. So let me go back. I mean, so that was a general, some general statements that I did in the case of a general ring A. I'm going to come back to the notation OP. So let me erase here. So first, what we have proved is that MP is generated by one element that I'm going to call TP. And TP will be a uniformizer at P. And now, because the intersection of all the powers of MP is trivial, if I take an element X inside OP, which is not 0, there exists n maximal such that X belongs to Mn, but X doesn't belong to Mn plus 1. And once you have this, you're done. Because what you're going to say is that you're going to say that the valuation of X, you're going to define it like this n. And now it is quite easy to prove everything, because what you have is actually that your X is a u times t to the n, where u is invertible. So using this, I mean, you can prove that the valuation of a product is the sum of a valuation, and that the valuation of the sum is greater or equal to the minimum of the two valuations. I'm not completely done, because now, I mean, I have defined the valuation for every element which is non-zero in OP. Well, it's not complicated. What are you going to do if you have an element now x, which is in k star? Then, I mean, it means that x is in the fraction field, so it's a quotient of x1 over x2, where the xe are in OP, and the valuation of x is just going to be valuation of x1 minus valuation of x2. And with this, of course, you can also prove the last part which is missing, that OP is exactly the x which have a non-negative valuation. Okay, so yeah, I mean, it's already like a bit involved in the sense of algebra. So it means that the property that we have described right now is an interesting property, okay? And so we are going to give a name to this valuation. So this valuation V, we are going to denote it the order at P. Okay, and it's going to be called the order at P. Okay. So let's look at two examples in order to see what is this valuation in two examples. As I said, I mean, everything is local, so I'm going to deal with affine curves here. So the first one I'm going to take is simply A1, and the point P is going to be the point 0 on A1. So how does OP looks like? So OP, I mean, it is the set of functions, so rational functions, which are of the form what? So f1 over f2 with f2 with fe inside the polynomial ring in one variable, and f2 at 0 is different from 0. And even it's easier to describe NP, because NP you want everything which is going to be 0 at your point P. And this is obviously the ring which is, the ideal which is generated by X. Okay, now what more? So we have this thing. So what can we say about the valuation? So the order at P of F. So let's say I'm going to take, so it has to be, so if F is written like, so sum from E equal 0 to n of alpha I xi equal 1 to m of beta I xi. I mean, the valuation of f is simply, you look at the numerators and you look at what is the maximal powers of x which divides the numerator. Or in another sense, I mean, the order at P of f is the max, or no, it's more the mean for I, such that alpha I is different from 0. Okay, so I mean, you recover the classical notion of what is the order of a polynomial. Let's take now a more interesting example, which is the case of a plane curve. So I'm going to take V, well, sorry, that's, so C of F, where F is a polynomial in K bar of X and Y. And so this is exactly exercise 3.2 in the notes. So then you should maybe stop here and try first to look at the exercise yourself. Okay, but now, so let me give a solution. So we take P, a smooth point in C of F. And the first thing, that you have to realize is that, well, after the change of variable, a linear change of variable, as we did the first time, we can move any point in the plane to a point 0, 0. And as this change of variable is an isomorphism, it doesn't change at all the properties of your curve. So after a change of variable, we are going to assume that P is the point with coordinates 0, 0. And you can even do a bit better. Now what you have done is that you have moved your point to the point 0, 0, but you can also, there is a tangent. It's a smooth point. So let's say the point was here on your curve with a tangent like this. What you have done is that you have moved your point to the point. So let's put an axis here. So you have moved this point to 0. And at the same time, you can rotate so that the tangent is going to be the line y equals 0. So I moved this, and at the same time, I rotate. And so, moreover, assume that the tangent at P is the line y equals 0. All right. So how, if I do all this change of variable, then I see that F has a precise form. F has to be a polynomial in X and Y. But now, if I look at the lowest term, first it has no constant term because it, at 0, 0 it must be 0. So there is no constant term. But also because y equals 0 is the tangent, it means that there is no x term. So I can always write my f as x squared times a polynomial, if I'm not mistaken. Yes, that's the right thing, times a polynomial h, minus y times a polynomial g. Okay? And now, this is quite nice because I want to look at m at the point P, the maximal ideal at the point P. So what are all the functions that are going to be 0, 0, which are going to be 0 at 0, 0? As there are functions in y, x and y, there must be like combinations of x and y. But now, of course, x at 0, 0 is 0, and y at 0, 0 is also 0. So it means that x and y are inside the ideal MP. But yeah, it can't really be much bigger than this, right? So you have everything like that. But we are not done, because we want something which is principal. So one of these two generators is too much. It can be expressed as the other one. So let's look. So locally, I'm working in the ring where I have inverted f, okay? Where f, I take the quotient by f. So if I work in k bar of x and y divided by f, then I can rewrite this expression. then I have x squared h minus yg, which is 0 inside this ring, which means that I can express y as x squared h over g. Where? Because now I'm inversing g. But what I say is that g at 0, 0 cannot be 0, because otherwise it would mean that y would not be the tangent. I mean, if you compute the derivative, it means that g at 0, 0 can't be 0. So if g at 0, 0 is not 0, I can invert it inside. So this is my ring O. And so this expression is inside O of P. And I'm done, because now what I have done is that I have expressed y as a power of x. So x is going to be my uniformizer. So this is a conclusion. So I can maybe write it here. So x is the uniformizer. At 0, 0. And what I have proved as well is that the order at P, so at 0, 0 of y, is at least 2. Because I mean, I have a 2 here, but maybe in my h, I could have also, again, power of x that could be, I could get out. So what I have proved is that the order at P of y is greater or equal to 2. OK. So that were the two examples that I wanted to show to you. And so as a quiz for you, you can try yet another example. Or let's say it's still a plane curve. So consider the curve C y squared z equal x cubed plus z cubed. And I'm asking what is the uniformizer at 0, 1, 0. Of course, I mean, you first you should prove that the curve is indeed a smooth curve at this point. OK. So let's come back to the more general situation. What we have is that any function on my curve, which is not 0, I'm going to be able to write it so at a point P, which is on C and which is smooth. I can write my function f as u Tpn, where Tp is the uniformizer. And with n, an element in Z, and u invertible. And what I see is that I'm going to define, thanks to that, the notion of zeros and poles. So a 0, so P is going to be a 0 of f if n is positive, and P is going to be a pole of f if n is negative. OK? So this is all what we did so far was locally. Can we try to say things that would be a bit more global now? And that's where projectives plays a role. Until now, I have not used this. I mean, I was looking at all my curves locally. So I mean, each time I was restricting to affine models. But now, I mean, projective is going to play a role. And I'm just going to claim the two following results globally. So for C projective curve, the first thing is that the number of poles is finite. So let f a non-zero element in case C, then the number of poles of f is finite. And if you apply the same argument to 1 over f, you see also the number of 0 is finite. Okay, so here, that's already nice, but I'm not really using projective. I'm using only the noetherianity of my rings. But here now I'm really going to use projective to say that if f has no poles or no 0, then f is a constant. Okay, so that's nice, and here you really use projective because otherwise you could like hide somehow your zeros or the poles at infinity, where you don't see the curve. You would have your affine curve, and then you would take the kind of compactification of your curve, the projectivization of your curve, and it means that all your zero could be hidden at infinity, and we don't want this. That's a very nice thing with projective. Directly, we see all the full picture. Nothing can be hidden. And so thanks to this, now that we have a finite number of things, we could define what we call the divisor of a function. And it's just a way to put all this information together. So it's a sum, a formal sum, over all the points of the curve, where you put the order at P of f times the point. Okay? And this formal sum is really finite because, this is not going to be 0 only for a finite number of elements on the curve. So this is a divisor. And so let me see if I want to do first this. Yeah. Okay. So now that I have defined the divisor of f as a formal sum here, I could also maybe define a divisor more generally. So a divisor is just going to be any formal sum of points on the curve where the NP are different from 0 for finitely many points. Okay? So this is a divisor. And what we have just said here is that somehow there is a map from the function field of the curve to the set of divisors, okay, which is the map that f maps to the sum, or to the divisor of f. Well, when one has a map, one always has the same kind of questions. Is this map, for instance, injective? The answer is almost. And almost that you can prove it in the following way. I leave it to you, this quiz. Proves that if div the f1 is div the f2, then f1 equal alpha f2 with alpha inside k bar, not 0. And actually it's an if and only if, but I need only this direction. So it's almost injective. Is it surjective? Can I obtain any sum of formal points like this as a divisor of a function? So that's the other direction. And the answer is not. That's another claim. is that if I compute the degree, so a degree of a divisor, so this is the sum of the NP. So this is not the claim, I mean this is the definition. The claim is that the degree of the divisor of a function is 0. Okay? In a sense, what you must think is that you have as many poles as you have zeros for a function. And I mean, I'm not going to prove that. I think I refer to the note. Let me see. That was proposition 3.3.1. So in chapter 3 of the notes. But I just want to try again to illustrate it in two simple examples. So let's take the case of C is P1. So the functions, I mean, they are the quotients of, so there are the f that I can write f1 over f2 with fe inside k bar of x, z homogeneous of the same degree. And now, so what are going to be the zeros and the poles? I mean, here I have a polynomials in two variables, but it means that I just look at either the point which are the affine, and then I put z equal 1, or I look at the infinity, which means I look at z equals 0 and x equal 1. So it is really more or less like just two polynomials in one variable. But you need to separate, of course, the point at infinity from the affine point. But modulo this fact, the zeros of a function here are going to be the 0 of f1 as a polynomial in one variable. And the poles are going to be the 0 of f2 as a polynomial in one variable. And of course, again, I mean, just the subtlety of maybe taken into account what happened at infinity. And now what? I mean, they are homogeneous of the same degree. And that's a nice point, because if they have the same degree, it means that the 0 of f1 and, I mean, the number of 0 of f1 and the number of 0 of f2 are the same. And if they are the same, it means that there are as many zeros as there are poles for these functions. The same can be done for a plane curve. I mean, for a plane curve, it's just that in that case, your function f, you're going to express it now as a quotient of a polynomial of two polynomials in three variables, but again, homogeneous of the same degree. And, well, maybe it's not a good idea. Maybe I should call it G. Because my plane curve is going to be a curve C of f. Okay? And now what? What are going to be the zeros and the pole of f? Again, I mean, the zeros, they are going to be given by the intersection of f of Cf with the curve given by Cg1. And the poles, they are going to be given by Cf intersection Cg2. And G1 or the Gi are homogeneous again. Huh? I mean, for projective curve, this is always mandatory, and of the same degree. Now, what do we do? I mean, we see that we are going to do the intersection of two curves. And the number of zeros is the cardinality of this intersection. So it means that it is the degree of f times the degree of G1. And the number of poles is the degree of f times the degree of G2. But G1 and G2 have the same degree, so these two numbers are the same, and we are done again. Of course, I cheated a bit. I cheated where? Because, I mean, you would need to count. I mean, for Bezout to say that the degree is indeed the product, the cardinality is the product of the degree, you need to take into account multiplicities. And they are defined in a quite subtle way. So in order to be completely correct, you would need to prove that when you look at the multiplicity of a point, it coincides with the order of the zero or the pole at that point. And so, I mean, this is like a local computation that you should do, of course, if you know precisely how to define the multiplicity in the sense of intersection, which I have not done. So we shall admit it for now. Okay. So all this to say that, yes, indeed, this map that was quite almost injective is certainly not surjective. But then, I mean, you could say, okay, well, I can't obtain all kind of divisor. But maybe I can obtain all the divisors of degree 0. So this is a subset div 0 inside all the divisor, which is the degree 0 divisor. And, well, in order to see this, what you can do is to take div 0 and quotient it by the image of this map, so by all the divisor of f. Okay? And you could see, I mean, if this, for instance, is just trivial. And the answer is, again, it's not trivial. And if you remember in the introduction of all the different courses, I said that there is an interesting object which is called the Picard group, or in that case, the Jacobian. And this is going to be the group which is of a very big interest. Of course, I mean, I'm not going to describe it now. I mean, this is going to come in the second part of the lectures. But I mean, it's a very interesting object, but you see its realization here. And somehow, it's really like to measure the difference between all the divisors of degree 0 and what are called the principal divisor, the divisor of a function. And, well, just, I mean, as a spoiler, I mean, this is never trivial. I mean, at least if the genus of the curve is not 0. Okay. So, I mean, with this, I mean, we have seen like plenty of nice properties of divisors, okay, and of the divisor of functions.